So these three different circuits are connected as shown here. All three batteries are ideal and have the same electromotive force of 6 volts. Remember, that's just the stupid word for the voltage of a battery. And all 5 light bulbs are identical and have the same resistance of 3 ohms. So in part A, we just want to represent each circuit as a diagram and then just state if it's a series or parallel circuit. So for the first one, we just have the battery with one bulb. So that's a very simple connection. Just draw the battery, loops around to one resistor, and back to the battery. We'll label that one as A. The second one, if you follow the path around the bulb, or around the circuit, comes out of the battery, goes through this bulb, and then through the next bulb, and then back to the battery. So we have 2 that are in series. So we'll draw the battery, and then B and C in series back to the battery. And for this last one, we can see that from the battery, it's going through, there's one path right there, but there's also a second loop it could take around E. So because D and E share common endpoints, they both come from this junction right here, and they both end at this junction right here. Those two are in parallel. So we'll draw the circuit for that one, showing the battery, and then one loop that contains light bulb D, and a second loop that contains light bulb E. So I want to rank the magnitudes of the potential differences across the light bulbs from largest to smallest, and justify the answer without actually calculating the potential differences. So if you remember anything about potential difference, you know that you have to measure it between 2 points. So let's look at this first circuit. We have to measure the potential difference across this light bulb. So if we connect it up here, and one part of the voltmeter is connected down here, the voltage from here to here would be the same whether we go across this path or whether we go across this path. Well, we know the voltage across this path is 6 volts, which means the voltage on this path would also have to be 6 volts. So A has 6 volts across it. Now I know it says to justify the answer without calculating the potential differences, so all we have to know here is that since it's just one single item connected to the battery, whatever the voltage of the battery is going to be the same as the voltage across that resistor. If we skip over to the third circuit, the same kind of thing happens. If I connect the voltmeter from, let's say, this point to this point, the voltage is the same whether I go on this path, or on this path, or on this path. So whatever voltage we have across the battery, that same voltage is going to be across each of the resistors. So we have the same voltage here, and here, and here. All 3 of those have the same voltage as the battery. So we can tie A, D, and E together for potential difference across them. Now on the middle circuit, circuit number 2, if I put a voltmeter connected between here and here, the voltage going from here to here would be the same along this path or along this path. But notice on this path, there's now 2 resistors, so the total voltage across both resistors combined will be the same as the battery. And we know that for things in series, the voltages have to add together. So the voltage across here and the voltage across here would add up to the voltage across that battery. Since these 2 resistors are the same, they are going to have the same voltage. If they were different resistors, if one had a higher resistance, it would just have a higher volt potential difference across it. But since they're the same resistance, they have the same potential difference across them, but it's half what the other ones are. So the ranking for potential difference across the resistors is going to be A, we'll say VA is equal to VD is equal to VE, and technically those should have deltas in front of them because we are talking about differences. So I'll go ahead and put them in there because that's probably how they do it on the AP exam. And then that's going to be greater than the potential difference across B, and C, which are equal to each other. And everything I said before that about was how you would justify the answer. Now in part C, we want to rank the magnitudes of the currents from largest to smallest. Well, we can use something that we picked up in Monday's class, and that is that as long as all the resistors or all the light bulbs are identical, the current ranking would be the same as the potential difference ranking. So that's the easiest way to answer this question, and then just say that the current through A is the same as the current through D, which is the same as the current through E, which is greater than the current through B and C, which are both equal. Just to get a better intuitive feel for that, you can kind of think of it like this. The first circuit, however much current comes out of the battery, all that current is going to flow through the light bulb and back to the battery. In the third circuit, there are resistors or light bulbs in parallel, which lowers the overall resistance of the circuit. Remember, in series, it increases the resistance, but in parallel, it decreases the resistance. So there's only half as much resistance, which means twice as much current would flow out of the battery. But even though there's twice as much current flowing out of the battery, when it gets to that junction point, that current's going to get split equally, half this way and half this way. So twice as much current being split in half ends up being the same amount of current going through D and E that went through A. That's why all three of these are equal. But now if you look at circuit 2, this circuit has more resistance because they're in series, so they add together. So more resistance means less current flowing out of the battery. So overall there's just going to be less current flowing through both resistors or light bulbs B and C. But because they're in series, the current is going to be the same for both of them. Okay, in part D, we just want to calculate the numerical values of the current through each light bulb and the potential difference across each light bulb. This is a pretty simple one to do without even drawing or setting up the VIR chart that I taught you before spring break. And that is that you can say the potential difference across A, that has to be the same as the battery, 6 volts. And we said that's also going to be the case for circuit 3, that the potential difference across D and across E would be the same as the battery, the 6 volts. That's why all three of those were ranked the same. But in circuit 2, the potential difference across B and C, they shared the voltage of the battery since they're in series. They added together, so each of those was just 3 volts. So those are all 5 potential differences, the numerical values. And you can see that it matches the ranking that we did right here. And now if we calculate the currents you have to do Ohm's law. So for the current through resistor A is going to be the potential difference across A divided by that resistance. The potential difference across A was 6. The resistance was 3. So the current across, or the current passing through resistor A, is 2 amps. Let's go to circuit 3 and look at that one. Now we said for this one that because they're in parallel, remember the way you add resistors in parallel is you add the reciprocals together. So it would be 1 over 3 plus 1 over 3, which is 2/3. But that's the reciprocal of the resistance. So you have to take the reciprocal of that, which gives you an equivalent resistance of that circuit of 3/2, or 1.5 ohms. So in circuit 3, the current through D and also the current through E is going to be the voltage across them. We'll say D, I'll just put DE, say the voltage across either one, divided by its total resistance, or the resistance of each one, and the voltage across them is 6, and the resistance of each one is, or the resistance of each one is 3, so that again gives you 2 amps. So notice that all 3 of those are the same, which matches our ranking. And then IB and IC, we want to get the voltage across. Let's just look at one of those at a time. So the voltage across B divided by its resistance, that would be 3 volts divided by the resistance of B, which is 3 ohms, and that gives you a current of 1 amp. So there's 1 amp of current flowing through B and 1 amp of current flowing through C, and it matches this ranking right here. Now we want to rank the brightness of the light bulbs from brightest to dimmest. You could do this without calculating it, but since we've got the calculations, it's pretty easy to do, because brightness depends on power, and the equation for power was I, the current, times delta V, the potential difference. So if we look at light bulb A, it's going to be the current, which was 2 amps, times the potential difference, which was 6 volts. So the power for light bulb A was 12 watts. If we do the next one, let's go ahead to D and E, since we know they're going to be ranked equally. That is, D and E have 6 volts across them, and also 2 across each one of those. So we can say the power of light bulb D and the power of light bulb E are also equal to 12 watts. And then finally we can do the powers of light bulbs B and C. Those are 3 times 1. So the power of B is equal to the power of C. 1 amp times 3 volts gives you 3 watts of power. So there's 4 times as much power in circuit 1, in each light bulb of circuit 1 and circuit 3 than there is in circuit 2. So that's why they end up being ranked in the same order. PA, PD, and PE all tie, and then PB and PC are tied for the last place. And part F, the batteries all start with the same amount of usable energy and are all connected to the light bulbs in the circuits at the same time. Rank the 3 circuits according to how quickly the battery will run out of usable energy. So basically, whichever one uses the most power overall is going to take the least amount of time. Notice in this part, we're not ranking the light bulbs, we are ranking the overall circuit, or just say, so this is just going to be a ranking between 3 items, circuit 1, circuit 2, and circuit 3. So, which circuit uses the most amount of power? Well, circuit 1 uses a total of 12 watts of power. We calculated that right here. Circuit 3 uses a total of 24 watts of power because each light bulb has 12 watts across it. That's 24 watts total. So I'll go ahead and label these next to the batteries. We said circuit 1 is 12 watts of power. Circuit 3 is going to be 24 watts of power. And then circuit 2, each bulb is just using 3 watts of power, and there's 2 of them. So that's going to be a total of 6 watts of power used up in that circuit. Depending on how much you remember from before spring break, you may remember that when you connected bulbs in series, like in circuit number 2, that they did show up as a lot dimmer, and that's why, because it just doesn't take as much power overall, but the bulbs in parallel were just as bright as a single bulb, because each bulb individually uses just as much power as the single bulb, but overall the whole circuit uses more power because there's two of them. So the order of ranking for running out is going to be circuit 3 is going to run out first because it has the most power, then circuit 1 will be next, and finally circuit 2 will stay lit for the longest because it uses the least amount of power.